This is Sciographies, an introduction to the people who make science happen. I'm your host, David Barclay. I'm an oceanographer with the Faculty of Science here at Dalhousie University. And on Sciographies, I interview different types of scientists about what shaped their interests, their career path, and how they get their research ideas. Thanks for joining us. In this episode, we talk to Dr. Chuck Macdonald, an inorganic chemist who completed his undergraduate and his PhD studies right here at Dalhousie. 2 years ago, Dr. Macdonald returned to his alma mater, but this time as the Dean of Science. As Dean, Dr. Macdonald is leading the charge to enhance science programming and facilities, but all while working to improve equity, diversity, inclusion, and accessibility within the Dal Science community. Dr. Macdonald is going to talk to us about growing up here in Halifax and how he became an inorganic chemist, and also why he enjoys tackling big picture projects as a university administrator. I would like to start with the fact that you are the dean.
Yeah.
And why did you want to become the dean?
Well, I guess when I started as a faculty member, within about 6 months, I was assigned to be a graduate coordinator for the department that I was in. So I'm a chemist by training. And so I had very, very early on really substantial administrative responsibilities and found that I could do them. I could still be a successful scientist and lead my group. And then the dean at the university that I was working at the time, at University of Windsor, so she left to take another role at Western University and tapped me to be an acting dean. Mm-hmm. And so then I had about a year of serving as acting dean. So I realized that I could do it. I realized that I liked it and that I could make a difference. And and for me, it really is that it gives you the opportunity to make change and to make things better if you want to, and to choose, to put resources and efforts into making things as best as possible for everyone.
And you went on to become the Dean of Science at Carleton. Yeah. And then you decided to come to Dal. Yeah. Can you tell us a bit about how that decision came about?
Well, for me, it's actually really easy because I'm actually from Halifax. Right. I grew up here. I did my undergraduate and PhD here at Dal back in the 90s. And so for me, it was an opportunity to come home and to, again, make a positive difference in a place that it will always be my home. And so it was really an exciting opportunity.
Now, before we go too far down the road, can you tell us a little bit about Halifax in the 70s?
I think, for me, it was a very, very nice place, to grow up. I played soccer and baseball and a variety of different sports. And that ended up actually, becoming a passion of mine for decades of, playing soccer and sports more generally. Yeah.
So where did you grow up in Halifax?
I grew up sort of by the Armdale Rotary.
Okay.
And chose to come to Dal to do undergraduate. I think really I'd liked all kinds of different sciences, but I had liked chemistry a lot in high school, and I guess I had forgotten about this, but there had been a contest that Dalhousie Chemistry had run that let people in, I think, grade 12, come and spend a week at Dal, and ended up winning one of the spots for that.
I like it's a contest. It was a secretly, you now know it's a recruitment.
Yeah, exactly.
But, you were like, do you remember what you had to do to apply?
I think we had to write an essay.
And so it was kind of a no-brainer decision that you were going to do a chemistry degree when you came here.
Well, it was, I think I always assumed that I was going to be a dentist, I think, when I was in high school. But
so close. You almost made it.
Yeah, but I think what happened, I'd taken physics and chemistry and computer science in first year, and I liked all of them, but I figured chemistry was the thing that I liked the most, and so I decided to pursue that.
Was it the lab work or the theory? What really got into you?
I think for me, it's the whole idea. And I think what I've always liked about chemistry more broadly is that, everything is made out of matter, and chemistry is really the science that lets you understand how that works and sometimes actually how you can change it. Right. And making new materials and making new things. And I really liked that idea of, sort of understanding. I like physics too, and I like math. I like all kinds. But chemistry for and it might have been my high school teacher that I had liked a lot, and really, I just enjoyed the subject, and I enjoyed that particular, I guess, approach to looking at problems.
During your undergrad, you obviously were focused on chemistry, but how did you get an appreciation for doing research, or how did that bug bite you?
Well, that was interesting because it was a different time. It really was before the internet really existed. And so it was actually some of my other, like the students that I went to school with, one of them said, you can get there's a scholarship that pays for you to do research in the summer. And so normally, let's say, since I was in high school, I'd always had jobs in food service. So I worked at Macdonald's on Quinpool Road, but the opportunity to actually do something that was going to be relevant to my career and what I wanted to do professionally was really exciting. And so I was able to get one of the NSERC undergraduate summer research awards, and I went and worked for Neil Burford, and it was great. I really enjoyed it. It was to actually be doing stuff that wasn't just it wasn't sort of a set lab where what the result is. It was actually doing something new and making something that hadn't been made before. And so that was really exciting. So I really liked that. And so then I did my fourth year honors project with him as well. And it was a pretty exciting time for that research group, because one of the gastroenterologists here at Dal had contacted him because people had just realized that there was a bacteria called Helicobacter pylori, which causes a lot of the problems that people have in their gastrointestinal systems, and that bismuth was potentially something that would treat it. And so this guy had looked up and found that Neil Burford was someone who might know how to do something with bismuth. And so as an honors student, I was one of the first people tasked with, can you make some compounds like this? And and it's because they wanted to see if they could kill the bacteria. And so we made a bunch of things, and me and one of the PhD students who just started at the time made a bunch of different compounds. And I guess for me it was exciting because that was a kind of science that actually had a goal in mind, a sort of a practical application as well. Although the things that I made would probably eat your stomach away worse than the bacteria.
And for those keeping score, importantly, this is an inorganic chemistry experiment, and I feel like that's basically like you like the Chicago Cubs or the White Sox. Like it's organic, inorganic. That split starts early.
It does. It really does. I mean, we do a lot of organic synthesis, and they are sort of complementary, let's say, subdivisions within chemistry. But organic and inorganic are very different in terms of how people think about making things. And so for me, I always liked the inorganic part because it wasn't as well understood as organic. So organic people have been doing that. People know how to do all kinds of different transformations in a very controlled way, and there are rules that you can follow, and there's and then that's what we teach people in second year and further on. Whereas for inorganic, a lot of things don't work the same way, and so you actually have to have people that come up with new ways to make things, or ways to make things in the first place. And so that's what I liked about doing it. So the kind of synthesis that I did and continue to do is sort of exploratory in that sense. We want to figure out how to do things that people haven't been able to do before, and to be able to make kinds of compounds or bonds or things that people haven't been able to do. And so it's discovering new chemistry and figuring out what the rules are for the rest of the periodic table, rather than just being sort of focusing on carbon and the organic elements.
And is it just a question of geometry? Like the geometries are different when you consider all these other elements?
It's not just geometry. It's actually the elements that organic chemistry is all based on end up actually being the exception to the rules that work for everything else in the periodic table. And so they work very well for organic, but that's not how everything else works in terms of how the geometries of bonds exist and what could be considered normal. But organic is so well known that everyone thinks of that as being the sort of standard, even though it's the exception.
Interesting. So with that experience, led right into a PhD in the same lab, or did you consider other labs?
I considered other labs, but I really, I liked what I was doing, and I liked the people that I worked with, and so I decided to stay. I mean, I normally have told my own students that they should go somewhere else and experience something different, but for me it was a very good situation, and I enjoyed the lab and I enjoyed being here.
And if I'm keeping track of time correctly, you did that PhD in 4 years.
Yeah.
Yeah. And you were working with iron, right? Is that right?
No, not iron. No, we did. I did most of my PhD was with, they say, phosphorus and arsenic and bismuth and antimony.
Okay.
Yeah. So that's what they call group 15 in the periodic table.
Yeah. Where does the idea come from to work with this group 15? Is this come from above, or is it something you were interested in, or is it just where the funding is, or how does that work?
No, it's so one of the main connections. So we were talking earlier about organic chemistry. Phosphorus ends up being very related in terms of its properties to carbon, and so all of the ideas that people have and all of the building and knowledge people have built up about carbon, one of the things that people have been doing now for several decades in organic chemistry is trying to figure out using phosphorus to make analogous compounds that have very, very different properties.
Right.
So, for example, I have friends that make polymers out of phosphorus that
Sure.
So whereas normal polymers will burn, and so if they catch on fire, they create problems. These things will actually, just by virtue of what they're made of, they don't burn, or they extinguish flames. And so you get very, very different properties by building things like that. And so people have used those kinds of ideas and the relationship between phosphorus and carbon to try to figure out, like, if we can build new things, if we can build materials with better properties, things that are safer. But for many of those elements, particularly some of the heavier ones, they're also very critical, and they're components in semiconductors and other things like that. And so if people want to be able to build new materials or dope materials or things like that, you need to have compounds and chemistry that actually lets you do that. And so there's always been a lot of interest in those elements.
Can you summarize for us a little bit what your findings of your PhD work were?
Well, so for my PhD work, what we were doing was trying to figure out how we could make compounds, again, sort of to mimic some of the really important organic compounds, which have what we call unsaturated, so they're multiple bonded compounds, which often, say, get turned into polymers or get turned into larger kinds of materials. But it's very difficult to make those kinds of compounds. Again, like I said, organic chemistry ends up actually being the exception. So it's easy for those ones, but it's not as easy for heavier elements. And so what we were doing was trying to be able to make compounds like that so that we could do additional chemistry to build molecules, containing other elements other than the organic elements.
Yeah. And that kind of research, for someone totally naive like myself, is it like recipe? Is it like baking? You're just trying different amounts of different ingredients to get the best cookie, or?
Well, it's thoughtful baking. Let's say. So what we have to understand is, what aspects of the molecules that we are designing can we change to have an effect that we want. And so actually, a lot of what we have done is play around with really the things that we have, like the groups, or what we call substituents, that are attached to, say, an element like phosphorus or arsenic. We can change their size and their shape, and it can force those elements to actually bind in a way that wouldn't normally happen.
Sure.
And it's a lot of what people have figured out how to do. And it can end up making things that are normally unstable, very stable, able to be isolated, able to be studied, and controlled.
So a certain aspect of that is doing computational chemistry?
Absolutely, yeah. And so we do a lot of that. And I was very lucky, I'd say, here at Dalhousie, is he was the chair of the department when I was here. He was Professor Russ Boyd, and so was a world expert in computational chemistry, and he taught me a class, and then actually let me use his computers, in order to start to address problems using both that sort of computational or theoretical side as well as experimental. And so I've done that now for my entire career. We use the combination of computational methods to either predict what it is that we're going to make, or to explain afterwards why it has the properties or the behavior that it does. But the other really key technique, which I was grateful to learn here, was X-ray crystallography, and that was Stan Cameron who taught me that course. And then when I was a postdoctoral fellow at the University of Texas, I had a really good opportunity to work there and actually run a machine all the time.
Okay.
And so it was great because the X-ray crystallography basically lets you get a picture of the molecules that you've made, and then you can compare that to what was actually done or predicted by the computers, and you can see how accurate that is. And again, then putting it all together to get a really good idea as to what would be the sort of next steps, or what you would want to change perhaps to get something different.
Right. So in this method, you're shooting X-rays at some compound and you look at the scattering to see what the spacing between the elements is, and kind of from all different angles you get a picture of what they physically are structured, how the structure looks like. Yeah,
it's great. It's a really, I mean, for me, that was always one of the most, and still is one of the most fun sort of techniques, because you have a very, very powerful beam of X-rays. You have to shoot it at a single crystal of a compound, but then the scattering pattern that you get, basically you can work backwards from that scattering pattern to figure out what the arrangement of the atoms actually had to be in 3 dimensions. And so it gives you effectively a picture of the molecule in the solid state. And the thing that's been nice sort of over the course of my career, so when I started, pretty much every instrument, they call them diffractometers, that would actually do these things, it would have to go measure every single spot one at a time. And so they called those things a point detector. But then CCD cameras, like what you have in your your phone, or these actually now have made big detectors that can detect hundreds or thousands of spots at a time. And so the collection time went from being like a week or more for a structure to being a couple of hours for some structures. And all of the software to figure out what things what things are, that's advanced amazingly. So you can have it almost automatically spitting out for something that's well behaved. You can have the machine will just tell you what the answer is very quickly, whereas in the old days that would be someone's entire PhD thesis trying to figure that out.
But you still have to make the compounds carefully by hand, and that's the real challenge. So you mentioned you went off to Texas to do a postdoc. So can you tell me what it was like to move to Texas?
It was really interesting. So where I was in Austin, and so I moved from Halifax in, let's say, I think it was July, and flew, and my plane had been delayed in Newark, and so I didn't get to Austin until the middle of the night. And one of the grad students came and picked me up, and when the door to the airport opened, it was like walking into an oven. It was absolutely, it was like 3 a.m. It was pitch black outside, but it was still 90 Fahrenheit. And he had an old Datsun with no air conditioning. And so, but very, very quickly you get used to the heat. But it was a really, really fun place. Austin is one place in Texas that's self-described a weird place.
Right. So how long were you in Texas? Pretty short-lived?
I was there for 3 years.
Okay. Bit of a stint. And
then
then the decision to continue on in research, not because I imagine there's a lot of industry jobs in chemistry that must be somewhat tempting.
No, absolutely. I mean, as I progressed, and particularly sort of at the end of my PhD, I realized that I liked academia. That I did actually like. I liked teaching. I liked mentoring other students and other people in the lab, and doing research that was self-directed, that I got to decide what I wanted to look at or not.
Sure. And you wound up at the University of Windsor right after that. And how did you build your research program?
So just as I was finishing my PhD here at Dal, there was a strike, and the students, myself included, got locked out of the labs. And so it forced me to write my thesis, which was good. But it also meant that some things that I'd had sitting in the lab just got to sit a whole lot longer than they would. And so when we came back, there were some crystals that were in one of the flasks that I'd gotten. And when I took them to Dr. Cameron to run the X-ray structure for, and he brought it back to me and he said, well, it's not what you want, but it's actually probably something much more interesting. And it ended up being something that was really almost unprecedented. And so I sort of kept that in mind over the years. And then when I was starting my own program, that was sort of the starting point for what I wanted to look at, was this very weird class of molecules that say they're very, very electron rich, and so they have very different chemistry than other things. And so that actually ended up working out quite well, and was able to build a program all around those kinds of things at the start.
So this is a material that has, you said, they're very electron rich and it gives
Yeah.
it different properties. What properties? What can it be used for?
You can do a lot of chemistry where those things that have extra electrons, they can be inserted into things, or they can very easily grow and make larger molecules. And so you can take the thing and sort of use it as a source of, say, just phosphorus, essentially, sort of like a phosphorus atom or an arsenic atom, and insert it in a controlled way to build bigger things. And sometimes it can be done very, very cleanly. And so we actually have some molecules that we built that now Alex Speed, who's another researcher here at Dalhousie, they found that our methods to build these things are the best there is, and then they can use those particular molecules. They use them to catalyze a whole variety of different reactions and do other things. But we develop the sort of building methods to build a lot of those kinds of things. And so they have unique reactivity that lets them do stuff that normally is very difficult to do.
Mm-hmm.
Yeah.
Okay. Yeah. So in terms of your time here at Dal, it's been about 2 years, and it takes a while, I'm sure, to get the lay of the land. What things have you identified as opportunities and changes you want to put in place for the faculty?
We've already started. I mean, so one of the big ones for me actually is equity, diversity, inclusion, and accessibility. And so I had done this at Carleton as well, but it created a position of associate dean for equity and inclusion. And that's really to address a lot of the problems historically that we've had in faculties of science. Science often has had substantial problems with gender as well as diversity more generally.
In terms of leadership, do you have a particular kind of style or mantra that you subscribe to?
I mean, I try to be very, very inclusive. I think one of the things, too, that I try to have teams where I don't want people to just agree with me. I like to have a diversity of opinions, and I want people to be free to express what they what they think about something, because I don't think I should be the smartest person in the room, and I certainly know in a faculty like science, there are experts in everything that we do that all know more than I do about that. I know about one little area of chemistry, and so I want and need people to participate. Let us know what they think we can do to make things better. And from my perspective, really, like what the office of the dean is actually supposed to do really is to facilitate things, to make it easier for faculty members and staff members and students to concentrate on what it is that they want to do or should be doing, and for us to help them to be able to do that as easily as possible.
In that sort of framework, it seems like the most important role that you have to play is to prioritize problems. And how do you go about making those tough decisions? Like, for example, you talked about how you want to facilitate students and staff and faculty to do their jobs, but then often, those things are in conflict, right?
Yeah.
For example, research versus teaching versus so how do you prioritize problems?
Well, I think, the biggest thing that I think we can provide that actually almost solves most problems is providing more time for people. And so often what I look at is what's the value of whatever this thing is that we're looking at, and can we change it to actually make it better by decreasing the amount of time people have to spend on things that isn't their biggest priority, and allow people to focus on the things that are their biggest priority. And so for faculty members, I think research and teaching, they're actually two facets of the same thing for us. So because within science, research is the medium through which we provide the best training and the most real experiential sort of training to individuals. And so we don't want to ever have the two things sort of at conflict with each other. And so we try to prioritize decisions so that that we can basically have people focusing on that, and maybe not having to focus on administrative or bureaucratic stuff, because we can cover that with other resources, or we can make things easier and provide more time for people to concentrate on those. Yeah.
And how about your strategy in terms of pushing upwards?
Yeah.
What messages are you kind of trying to focus on for the next little while in terms of to the community, to the upper administration of the university, and to the funding agencies?
Well, I'd say like so some of the bigger things. I mean, we need more space and better space, to be able to we are already the largest faculty in terms of student numbers by far at the university, and we continue to grow. And we do need facilities and people to do that. One of the other big things that I think is and continues to be a passion of mine is actually interacting with the community more widely and communication, because I'd say I sometimes paraphrase there's an old NCAA ad. They say most of our students go professional in something other than academia, and so they're not going to be faculty members. Most of them are going to go work for a company or work for the government or work in some other sector, and so we should make sure that we're training people that are able to do that, and to communicate with people that are in those other areas, and so I push for us to be able to have more things like communication certificate and other kinds of training that enhances what our graduates can get, and so communication is one area, but I like that more broadly, because I do think that particularly over the last at least decade or so, the loss of trust in scientists and experts is a serious problem that faces our our world, and we need to. I think it's incumbent upon us as scientists to actually go and talk to the community so that we can explain why it is that we do what we do, why it's important, how it's going to help.
You talked about that. One of the things you're passionate about is sort of community outreach, community engagement, and we talked about infrastructure. So what infrastructure are you building to increase community engagement in the university?
Yeah, well, I do think one of the most exciting projects is the BD Center for Marine Biodiversity, for a variety of reasons. So I have two boys, 13-year-old and 10-year-old, and we love to go to places like the Discovery Center and museums, and especially where they're interactive. And so this is what the BD Center is going to be, something like this, where we have here on the campus at Dalhousie displays that children or people who are interested of all ages will be able to interact with and learn about what they can do to try to help the problem with losing biodiversity, and showing what we do here at Dal in terms of research and training, and from the really fundamental perspective, what we're contributing to being able to solve problems of biodiversity or to address those kinds of concerns. But this will be a real showpiece kind of facility that'll be fun. And I remember I always liked, and still do, like going to museums and aquaria and stuff like that. And so I think that this is going to be really, really neat. We will have pretty sizable aquarium space, which is really exciting, I think, for Halifax and for Dal. So. Yeah.
Okay, well, thank you so much for coming in today. It's been really interesting hearing about everything, and really appreciate your time.
Well, thank you so much. It's been a pleasure.
In our next episode, we'll talk to Dr. Shannon Sterling. She's an environmental scientist, hydrologist, and startup founder working on carbon dioxide removal technology. If you're enjoying Sciographies, hit the subscribe button, maybe give us a rating. I'm your host, David Barclay. Thanks for listening. Sciographies is brought to you by Dalhousie University's Faculty of Science and CKDU 88.1 FM in Halifax, Nova Scotia. Our producer is Nicole Killowy. You can learn more about Sciographies at dal.ca/Sciographies.